So in this tutorial, we're going to have a look at what I personally think is a fascinating aspect of our subject, and you might be somewhat freaked out to realize that I do in fact actually kind of do this stuff for fun, which you might think is a little bit odd, but I don't know, I find it like a really intuitive and enjoyable skill, and hopefully by the end of this tutorial, about 10 minutes time, you're going to also feel the same way about it. So look, let us define our key terms first of all. So we clearly have to understand what the concept of force is. So let us make it absolutely clear. A force, so, you know, the pure definition of this thing is make sure you're getting this down in your notes, please, is a push or a pull. Is a push or a pull. Is a push or a pull. And the blue stuff is kind of like the really critical stuff. That's why I'm putting it in blue. That, and this little statement I'm going to make here, I think is a really fascinating one for me personally, that tends to change the motion of a body. So look, I mean, you need to kind of study that in terms of the definition of it. You know, these are the words that you need to write down in an exam kind of situation. But much more than that, just think about that concept. A force is simply something where we say, if we apply a force to something, the motion of it tends to change. Okay, so have a look at something that's around you, a book on the table, or a mate that's next to you. Just lean on your mate, or just apply a force to the book. What does it do? It tends to change its motion from being stationary to moving, right? That's all that means, okay? But the other thing is this word tends is also very interesting, because what we're saying here is the force needs to be large enough to overcome the inertia of the object. So don't forget this concept of inertia. Of course, it relates immediately back to Newton's first law. If an object has either a lot of mass or a lot of velocity or both, then it's hard to change its inertia, its state of motion. So therefore, we'd need a larger force. But by definition, this is what we're talking about. Now, what I'd also like to address with you guys today is the idea that we measure a force. It's measured in, and I'm hoping you're kind of screaming at the screen here, it's measured in newtons. And I'm sure you've learned this in kind of year 7 or year 9 physics kind of lessons. And the unit measure, the unit symbol is at capital N. Okay, so we measure it in newtons. But the thing I'd like to really address with you is that any force has kind of two properties. Property 1 is that the force has a direction. Okay, so the force is applied forwards or backwards or clockwise. That would be a torque, actually, not a force. But anyway, the force is applied to the left. It's applied to the northwesterly, that kind of situation. But also, of course, a force has what we'd call a magnitude. And by magnitude, this is like just a posh word for saying size, magnitude or size. So in other words, some forces are larger and some forces are smaller. Over here, some forces are applied in one direction, some forces are applied in another direction. So of course, I'm hoping this is kind of intuitively obvious to you. You know, if you want to prepare, let's think about that book that I imagined was on the table next to you. I've actually got a book on the table next to me. Let me grab it. So I've got this book. It's by Naomi Klein. It's called No Logo. Good book, actually. Anyway, I'm going to apply a force to it, and I'm going to try and propel it forward away from me. So, of course, what do? Is I apply enough force to move the book, and I apply it in the direction. So I've applied the magnitude, and I apply that force in the direction that I want the book to move. Okay, so that is what so the magnitude needs to be big enough so it tends to change the state of motion, and it needs to be in the direction which we intend to propel the object or whatever it is we're working with. A couple of other points, and it leads straight on from this really. I'd like you to get a grasp for the difference between a vector, so here's vectors over here, and what we're going to start referring to as of now as a scalar. Okay, vectors and scalars. And don't worry at all if you've never heard of these terms before. The first thing I'd like you to develop in terms of a vector is I'd like you to realize it can be illustrated with an arrow. Okay, so I want you to think about what that means. By definition, that vector has a direction because the arrow is pointing somewhere. In this case, it's kind of pointing up here, right? And it has a magnitude. And I'd like you to think, what magnitude does this arrow, this vector have? And if you measured the arrow in terms of its length and you said, right, however long it is the magnitude, you'd be absolutely correct. Now, any of you that study mathematics or physics to a higher level, you'll know about vectors and illustrating vectors on graphs, for example. So this won't be new to you, but we're talking about this arrow having both, and you'll see why in a second, both direction, up there, and magnitude, it's this long. Okay, so that should make sense. Whereas a scalar is something completely different. A scalar is simply a number. Okay, so if you think about what a scalar has, it has magnitude, maybe, it mass, we have a mass of 10 kilograms, for example, but we don't know in which direction that 10 kilograms is being applied until we convert it into a weight. So vectors and scalars are different. And all I'd like you to grasp at this point is that vectors include the following. Vectors are force. They are weight. Force in general. Weight, of course, is a force. They are momentum. These are example of vectors that you could effectively illustrate with an arrow at some point. So vectors are force, weight, momentum, things like acceleration, because of course we've got acceleration in a particular direction. Velocity is a vector. We could also include in here things such as reaction force is a vector. We could also apply in here that we've got things like air resistance is a vector, more of which in a few moments' time. Air resistance is a vector. We've also got things like thrust, buoyancy, drag when we're, say, in water, swimming, for example. But another one is what we call displacement. Now, displacement is kind of like distance in a specific direction. I mentioned kind of northwesterly, southeasterly, this sort of concept. Now, a scalar, we're dealing with completely different terms here. A scalar is things like mass. Now, let's say that I have a mass of 80 kilograms. Say, I wish. Let's say I had a mass of 80 kilograms. That is a scalar. It's just got scale or magnitude. Speed is a scalar because we do not know what direction that speed is going in. Distance is a scalar because, again, we don't know what direction it is traveling in. Energy is a scalar, and energy is simply a number. So what I want to do now is I want to focus on these vectors and start to show you how vectors can actually be illustrated. Now, I've actually got some images I thought I was going to get further down the canvas. I've got some images here that we're going to work with. In fact, I'm also going to get my toolbar up on the screen as well, because this toolbar is going to help us in a second. So I'll bring this down here because we're going to use some nice straight lines. So look, first of all, let's look at our example number 1 over here. We've got Roger Federer, and basically, how would we describe this position? We kind of say he's in a ready position, right? He's stationary, he's not moving. So we can start to illustrate the forces acting on this individual. So what I'm going to do is I'm going to make some lines. And the first one, let me choose a nice kind of red color. I'm going to illustrate Roger Federer's vector. Well, this vector here, I'm not going to tell you which one it is just yet. I'd like you to kind of try and figure out what vector this is. Okay, and what would that vector be acting straight down to the center of the Earth? Well, of course, if you're screaming at the screen that this is the weight vector, remember we said weight up here was a weight up here was a vector, don't forget. There it is there, weight is a vector. This, of course, would be the weight vector for Roger Federer. Now, on this illustration, what this pin diagram or vector diagram is showing me now, as I leave it in that state, is that Roger Federer is sinking into the ground, because if there was only the down force, the weight force acting to the center of the Earth, this performer would move in that direction. They would accelerate in that direction. Remember the application of Newton's second law. So, of course, what we have to do is we have to say, right, well, there are other forces acting. So here is one of those. I'm going to try and be as accurate as possible. And here is another. Okay, so let me get rid of that. So now they're meant to be vertically upwards, by the way. I'm kind of free-handing it. I hope you're being very specific. Now, I don't know if I've done it perfectly, but the idea here is that if you take this green vector here and this other green vector here, they are together combined roughly, and you'll do it exactly with your ruler, by the way, the same length as the weight vector. And we're going to label this GRF. And this one, GRF. And that stands for, I'll put it over here for you, that stands for ground reaction force. You can just put reaction force, it's absolutely fine. Ground reaction force. Now what we can see now in this illustration is effectively that GRF equals weight. Would you agree with me? GRF, the two GRFs combined, equal the weight. They are opposite in direction and they are equal in magnitude. So the result of this is that we're in a situation, let me just come down slightly further, we're now in a situation where we would describe this as 0, 0 net force. Now net, all that means is total force, 0 net force. So we could also say here that we have a situation of no movement. Now the other alternative for me there was that we had constant velocity, but constant velocity and no movement can be the same thing. We have a constant velocity of 0. Of course it could be a constant velocity in the sense that we're at maximum speed. I'll show you that perhaps in a second. Well, not maximum speed, but a set consistent speed. So here we've been able to illustrate that ground reaction force and weight cancel each other out, and therefore GRF equals weight. We've got 0 net force acting here. Now the second example, I'm going to make an assumption here. Let's change the situation. Let's assume that this person is accelerating, okay, just for argument's sake. And of course their acceleration is going to be what we call horizontal acceleration. So the first thing we always have to do with our vectors, if we've got movement, we always, in fact let me do it with a straight line, we always have to provide a little arrow like that, and we call that the DOM arrow, the direction of movement. Now this one doesn't have one, of course, because they're not moving, but this performer is moving in that direction. We always need to incorporate that. But now what we're going to do is we're going to illustrate the vectors for this performer. So first things first, let's keep it simple. This person has effectively, maybe slightly less because they might not be as heavy as Roger Federer, but they have a weight vector. That should not surprise us from what we just looked at. That's there. Okay. Now, by the way, I'm assuming the foot is on the ground. I think, if we're being really honest, the foot is just off the ground, but I'm going to assume that foot is just touching the ground here. So what do we have? We now have a situation where we have, oops, that was not what I meant to do. Of course, let me take my straight line. We now have a ground reaction force arrow. There's only one foot on the ground, which is equal and opposite to the weight force. So would you agree with me again that in this illustration, ground reaction force again equals weight? So again, they're not accelerating upwards nor downwards. So you might be saying to me, but James, you said they are accelerating horizontally. Well, let's illustrate that now. We have some horizontal forces acting on this body. I should have stressed, by the way, that this is the center of mass, and we would always illustrate weight from the center of mass. Likewise, we'd always illustrate ground reaction force from the contact point between the foot, say, assuming it's the foot, it becoming a hand in a handstand, and the floor, okay, and the ground. So now we want to have a look at our horizontal forces. Now we've got acceleration. So let's think about what the forward force is here. Well, I'm going to use an orange vector, and I'm going to illustrate from here, and I'm going to illustrate one line forward like this. And I'm going to label that F. I want you to think what F is. F stands for friction. Friction is the anti-slipping force. So if her foot was going to slip, it'd sort of slip in this direction, right? So friction opposes that. And one of the ways we can increase friction is by having like grippy or even spiky shoes, especially in athletics, track athletics, or in other sports we use spikes as well, cricket, golf, these kind of things. So the friction arrow, the forward horizontal vector, is relatively large. Now then, I'm going to say, we'll go for a blue vector this time. I'm going to say that the one I'm illustrating now, this one, which we're going to label AR, is smaller. So can you now see from here that what we've got is we've got a situation where F is greater than, which blue did I choose? AR. Friction is greater than air resistance. And what does that mean? It means that we're symbolically, that's all we're doing, symbolically illustrating forward acceleration. Because friction is greater than air resistance, all I need to do is look at this whole image and it shows me clearly that this performer is accelerating. Now, could you tell me, let's say we had a shorter arrow, let's say the friction vector only came to here, say, could you tell me what we would have now? Friction and air resistance would equal each other, and we'd have constant velocity. We go zero net force. If air resistance, if this person happened to be running much faster, and air resistance all of a sudden was bigger than friction, could you see that we'd have deceleration? Because friction would be smaller than air resistance and we'd have deceleration. And this is how we show, in fact, we calculate resultant forces. Now, last thing from what is already a fairly lengthy video is I would simply add on to this that we've got to also be aware that sometimes we need to take a scalar, such as weight, and we need to convert it into a vector, such as mass, and we need to convert it into a vector such as weight. So mass is scalar, weight is a vector. How do we get from one to the other? Now, in the case of weight, let's say that we've got an object which is 10 kilograms. Let's actually draw it in here. Let's sort of make some kind of 10 kilo weight on here, okay? So this is applying 10 kilograms, or this has a mass of 10 kilograms. But the thing is that 10 kilograms of mass does not have a direction. We actually have to multiply that by gravity, which of course always acts to the center of the Earth, to get the weight vector. So of course what we're going to do now is times 10 by 9.81, which is meters per second squared. And what we're then going to get, of course, is we're effectively going to get, let me get this right, we're then effectively going to get 98.1 newtons. So that object with a weight of 10 kilograms is going to apply a weight vector, a weight of 98.1 newtons. And that's how we go about calculating weight. Now, you might want to measure your mass, whether you're 50 kilos or 100 kilos or anything in between, and then calculate and multiply it by 9.81 and get your weight force that acts downwards. And the only thing I'd say is that it's never too terrible if you multiply mass by 10. I see 9.81, it's pretty close. Very often in basic mechanics, we'd multiply by 10 to get an approximate application of force. That's all from me. Bit of a lengthy one. Thanks for paying attention. All the best.